So the first question is, why would we construct a profile from a contour map? Well, some reasons are that it's visually easier to see topography in a cross-section or a profile than it is for most people anyways when they're looking at a topographic map. Another reason is that we can use vertical exaggeration. Now you've seen in some of the other labs using Google Earth how you can use vertical exaggeration to stretch things vertically, but we can also use it to compress things depending on our needs. We can also use these to help determine how beds and formations are oriented. So how do we do it? If we have our contour map, it looks something like this. We'll mark a transect line, and that's where we want to create the profile. That's, as the crow flies line across the topography. That transect line is kind of our guide. What we're going to do is take and lay a piece of paper across it. Now instead of using this diagonal one, I'm using this highlighted one across the bottom here. And so I have my piece of paper laid right along that transect line. And I start making tick marks anywhere that a contour line touches my paper. Now I have to label those tick marks, otherwise they're fairly meaningless. And so I can see, like, this is labeled a 50-meter high contour line, so I have my tick mark labeled 50. I know this is going uphill, so this is a 75 and a 100, and so forth. On your map, it may be a different contour interval, so you have to pay attention. If you have every fifth line is bold to help keep track, that'll help a lot with making your tick marks. At this point, you don't have to worry about any kind of dip or angle or anything like that. Just make the marks and get them labeled. And then you can set that paper aside for a moment and you make your plot area on a fresh sheet of paper. You want to make sure that your vertical axis extends at least far enough to cover your minimum and maximum elevation lines that you just marked on that first sheet of paper. It's okay to have a little bit higher, definitely okay to have lower if you're going to be doing a cross section as well as the profile, because you'll need some underground space. And you also want to make sure that you're doing your vertical axis based on your vertical exaggeration needs. Now, how do you do that? Well, first, quick review on what vertical exaggeration is. It's the ratio when your vertical scale, your vertical axis, is different than the scale on your horizontal axis. And we write it as a multiplier. This is done so that we can see features in the cross-section that will be difficult to see otherwise. This becomes very important if, for example, your cross-section is very, very long. Suppose you're doing a cross-section of a 200-mile transect across a mountain range. If your vertical scale was identical, your mountains would hardly show up at all because they're not 200 miles long. They're 200 miles long, but they're not 200 miles high. Their height relative to your length is very, very minimal. Even for shorter transects, you can use vertical exaggeration if your topography is very flat. For example, if we were doing a profile of Grand Forks, North Dakota, we would need a fairly high vertical exaggeration to see anything. But we can also use it when the topography is very extreme, like, for example, the Rocky Mountains. As long as we're not doing a really, really long transect, the elevation change relative to the horizontal distance might be so extreme that we need to compress it some and have a small multiplier like 1/2 or 1/10 to compress it enough to see what we're looking for. So how do we do it? Well, we can go about setting our vertical exaggeration in two ways. We can choose our vertical exaggeration and make our scale bar accordingly, or we can simply draw our vertical axis and measure it and calculate the vertical exaggeration that we just created. So, okay, how do we calculate it? It'll depend on how the map scale is written. Map scales can be fractions, or ratios, or equivalencies. So if it's in fractions, like you have a map scale that says 1 inch divided by 50 feet, letting you know that every inch on the map relates to 50 feet in the real world. On your vertical scale, you'll have feet marked, and you'll have actual physical length on your scale bar, or on your vertical axis rather, where if you throw a ruler down and you measure 1 inch and you see it's 200 feet, then that vertical scale will be 1 to 200, or 1 inch to 200 feet. Now, as an example, if our vertical was 1 inch equals 50 feet, and our horizontal was 1 inch equals 200 feet, we would do the fraction 1 over 50 divided by the fraction 1 over 200. This comes out to 4. You notice all the units cancel. The inches cancel out and the feet cancel out. It's okay if they're not all 1 inch and something feet. If on your vertical axis you measure the distance for 50 feet and it comes out as like 1.2 inches, you can put 1.2 divided by 50 feet. That's fine as long as the units match up. If on the other hand your scale bar is set up as an equivalency, like 1 inch equals 50 feet, all you have to do is convert it to a fraction, make sure that your horizontal and vertical scale bars are using the same units, convert if you need to, and then do it exactly the same way. So if the vertical scale 1 inch equals 50 feet, horizontal 1 inch equals 200 feet, you come up with the exact same fractions. 1 inch over 50 divided by 1 inch over 200 equals 4. And then the other common scale shown on maps is in the ratio form, 1 to 50. This means that 1 inch on the map equals 50 inches in real life, or 1 foot on the map equals 50 feet in real life. It's not shown with units because you can use any units with that ratio. But all you have to do is convert to fractions, still no units. So 1 to 50 becomes 1 over 50, 1 to 200 becomes 1 over 200. Set it up the same way and you get the same result. In this case there are no units to cancel out, you just get 4. So you can see that regardless of which of the three ways your scale was written, if the numbers are the same, the ratios are the same, you get the exact same vertical exaggeration. The way you write it is always the same. It's the number followed by a capital X. It's the same way you'd write like magnification from a microscope. So that 4 becomes a 4x, vertical exaggeration of 4 times, or 4x. If we have a vertical exaggeration that's compressing it, like 0.2, we would write 0.2x. That's our vertical exaggeration. That means that the vertical scale is 5 times smaller than the horizontal scale. So in this case, I just have my vertical axis where my feet are on the blue lines because I'm using lined paper. So I would need to put my ruler on here and measure, for example, how high 50 feet is, and use that in my vertical exaggeration calculation. Now, right here I have still images. Later on in this recording, there is a live video, and in part of that live video, it shows straight through making a profile from a topographic map. So you can watch that to see it being done, but to just describe it, you want to line up the left side of your transect line that you've marked on your paper with the vertical axis. Like you can see here, the A is lined up with the vertical axis. And then you can transfer these different elevations onto your paper as dots. You can slide it up and down, keeping the A on the axis. And so now my 75 is right along and connects, put a little dot at the 75. I can slide the paper up, put the dot at the 100. That way you don't have to guess that you're going straight up and down. You just slide your paper right along the axis. Much more accurate. Once you're done transferring all of your data points, you can play connect the dots. Keep in mind knowledge about hills and slopes. Generally there's a little bit of rounding, but not absolutely always. There are sharp angles in nature, but a lot of times if it's a hill slope, especially if you've seen the hill slope and you know, hey, it's round, or hey, it's sharp and jagged, draw your profile to match. Now we'll look at taking that a step further and actually doing a cross section. We'll start with a simple one that has a flat surface, and then one that uses a profile and draws the layers under that profile. So the first question might be, how is a cross-section different than the profile? Well, the profile shows the surface of the land. The cross-section shows the rock layers underground. To start a cross-section from a geologic map, whether you're given the geologic map or whether you make it yourself like you might do in field camp or on the job, you're going to start just like you did with a profile map. Mark a transect on the map, a straight line, label the endpoints, and then lay your paper along that line. Mark the ends of your transect on your paper, and then start marking the different rock unit contacts wherever it changes color or pattern. Mark any dips that you know, like this is a 30-degree dip, and these lines are actually dipping in that direction. Over here, we start dipping to the left. This plus mark is a 0 dip, so that portion of the rock is not dipping, it's horizontal right there at the surface, and so I've got it labeled as 0. And you go on and you do that for all of your contacts. So far it looks very much like the profile elevation lines. The main difference is the tick marks are dipping in the direction that the beds are dipping. Now, if when you're creating your plot area, your ground surface is flat, you can just draw a straight line across the top that connects to your vertical axis, and that's your ground surface. If, like in part 3, you have a surface profile, don't draw the line across the top. You'll make your dotted line and create your profile before you go in and add your geologic beds. Now, again, the video that's coming up shortly, embedded in this video, will show you step by step how to do this. This is just the basic description. So now that you have all of the surface contact points drawn, either on your flat surface or on your profile, you need to start connecting them and extending them underground. If there were symbols on your map, you'll know if the beds are dipping, at what angles they're dipping, but a lot of times you don't have symbols. If you've made your map out in the field, unless at an outcrop you could actually tell what angle a bed was dipping, you're not going to have that. You're going to have to use things like the ages of the rocks, the pattern of exposures that you see, the types of rocks that you see, and any other information available. Maybe you've got a well that was logged that tells you some about the layers going down right there where the well is. Combine any data that you have to figure out which direction the beds are dipping, roughly what angle they might be dipping at, and then draw your cross section from there. In part 3 of this lab, you don't have dip symbols. You have ages of the rock that have been determined and given to you, labeled. Those are the letters on the different rock units. And so that'll tell you what's older and what's younger if you look at a geologic time scale. And you see a surface pattern. Some of the rocks have that open angle shape that tells you, hey, I've got either a dipping anticline or a dipping syncline. Then add in the age data and you can figure out what you've got going on and use that kind of information to draw your beds in your cross section. If you've got angles, make sure you use a protractor and actually start your beds at the proper angle. You don't need to draw the line really far, because as you know, if you think about an anticline or a syncline, the angle doesn't stay constant all along the limb. It changes as it reaches the apex of the fold, and along that hinge line, it levels out and then goes down in the other direction. But at the surface, you have a dip angle, so you want to get that correct. And then you can see in this little example here, it's obviously some kind of a syncline feature, and I can extend them down and connect the matching bed type, like the B with the B and so forth. Now, one key thing, and you have this in part 2, is if you have a fault, you may not know exactly what angle the fault is dipping, but you may or may not have the direction that the fault's dipping from your survey work or from your map, but you can use the sequence of bed exposures to figure out which way it's dipping and if you have a normal or a reverse fault or even a transform fault. So then go ahead and once you've figured that out, draw it in. If you don't have an angle, go ahead and do a little bit steeper than a 45 is fine for your cross section. If you've got information about it, of course you want to put in the accurate, appropriate angle. Make sure all your rock contacts stop at the fault, that they don't cross it. The definition of a fault is that there is an offset. The rock has moved. Otherwise, it's just a crack and it's not a fault. So, the rock bed on one side of the fault will be on the other side, but it'll be offset, so you can't just draw straight across your fault. Also, make sure that your beds actually end somewhere. They can't just be open and vague. They have to reach the edge of your cross-section, or reach a fault, or pinch off somehow. And once you're all done, make sure you label things. Provide a scale bar for the horizontal scale. If you've got a profile, then of course you're going to have your vertical exaggeration, and provide a key or legend to show your rock types, whether it's patterns or colors or abbreviations. You want all that information available. Don't assume that whoever looks at the map knows exactly what you were thinking when you made it. And then also label the ends of your transect lines. So with that, we'll segue into the live recording, and you should be all set to complete your lab.